Okay, so, oh, hang on. Let me mute myself. Okay, so this is just going to be a test video. I've been wanting to do some streaming for a while, uh, on some topics that I know something about and have wanted to make some videos about. Um, but I have no plan for this. So we're just gonna kind of treat it as a test. Um, expecting to keep this pretty short. It's already kind of late, but I wanted to talk a bit about Verilog, and specifically, you know, what makes Verilog interesting to a programmer? So you might know something about software, you might know something about programming languages, um, but why would you care about uh, Verilog? And if you don't know what Verilog is, it's a hardware design language. Sorry, I'm also kind of trying to up the size of my text at the same time. That didn't work. All of these programs are new to me, so uh, it's maybe all of this is an all of this is an experiment. Wow, yeah, I really have no idea how this works. Why? There we go. Here. This is one of the most annoying interfaces you could have made for selecting font, so nice work, Zernal. Otherwise, it's been pretty nice so far. I don't mean to trash on it. So, why is Verilog? Oh man, I don't even have standard text moving around capabilities. That's very annoying. So what makes Verilog interesting to a programmer? And why, might as well just switch over to using the pen here because I have it. Um, so why is Verilog interesting to a programmer? Well, one thing is that, it looks like a programming language. And yeah, my handwriting is terrible. It always has been. I'm hoping that this is kind of an exercise to make it better. It would be nice to be able to write both fast and neatly. And right now I do neither, so hopefully I'll get better at doing this. Um, so it looks like a programming language, but it's not. And there's a lot to learn from looking at something like this, even if you never plan to write any Verilog in your life. And honestly, you'd be better if you never did. Um, there's a lot to learn from at least looking at it, understanding it. You can kind of think of it like, you know, learning TensorFlow, or SQL or Haskell. A lot of these things are, SQL is super useful. I mean, TensorFlow is super useful. Haskell, we like to think it's useful, but um, not necessarily. Uh, no shade on Haskell people. I love Haskell, but these are all very different programming styles. So, like TensorFlow is kind of a declarative, graph-based thing. SQL is also like this. SQL is a query language. It's also a little bit more declarative, and then obviously Haskell's functional. And if you learn if you learn something about these different languages, you can kind of carry the techniques of those languages, what's good about those languages, over to uh, the language that you are using. And most of us write imperative. So Python, probably for most people, Python or TypeScript. Maybe some of you C, most likely C++ or Java at the system level. Maybe some people are Rust. Uh, you know, all of these are imperative, and they can have functional, or declarative elements to them, functional declarative features inside of them. Um, and so, in the same way that learning Haskell or learning SQL, learning TensorFlow helps you bring, you know, you can bring something to using C++ or using Java, using Python. In the same way, there might be some kind of transfer learning from Verilog over these languages. I think that's a kind of a tenuous argument, but I'm gonna roll with it because I'm making this video. At the very least, as an answer to why, it's honestly it's just fascinating. It's just an interesting language. It's actually pretty simple, the core of it. In the same way that C++ is a beast, but kind of the C heart of C++ is a very, simple and beautiful language in a lot of ways. Has a lot of sharp edges, has a lot of extra features, but kind of core is very nice and comprehensible. In the same way, Verilog is very nice and very comprehensible, and it's capturing something that all of us can really understand. Um, it's just in a completely different domain. So maybe let's just go ahead and start with, the highest level 10K foot view. Um, so, Verilog versus the world. By world, I really mean like software. Stuff that, you as a programmer, if you are a programmer or if you're a hobbyist, stuff that you'd be encountering. I mean, the highest level difference is that, this is for hardware. Verilog is for developing hardware. And, these are for developing software slash everything else. And so what does it mean? What does this mean? Not just what does hardware mean, because I think that is an important question, but like, what does it mean that the language is for developing hardware? Like, what does developing hardware actually look like? Well, it turns out that developing hardware actually looks a lot like writing code. Not just in the sense that, and this is maybe obvious because Verilog is a programming language, right? Like you write it in an editor. A lot of people use VS Code. A lot of people use VS Code plugins. A lot of people use GitHub CI. Like all of these things carry over between the two. So, at the surface, they look very similar. But, even as you drill deeper down, there's a lot of similarities. So like surface level, oh man, I hit this bug before with Zernal. I should need to turn off the scrolling. Surface. Oh, there we go again. I gotta rotate the pen in my hand. Okay, let's just clean up this mess a little bit. So surface level, editing, CI, etc., etc. But then, like, let's drill one layer down. Like, what is the cycle, the development cycle? Development cycle. There's, similar to writing programming, you're writing tests, benchmarking, deploying, documenting, all of this. There's some big differences here, but the life cycle is really the same. You're doing a lot of the same thing. The big differences are really in maybe two examples. Number one, testing is far more rigorous. Why? Because chips cost a lot of money. So all this code you're making eventually gets turned into silicon in a process that's going to cost hundreds of millions of dollars. It depends on the run. That could be an over or an underestimate, but depends on how many chips you're making, whatever. But it's a lot of money per chip. This isn't just like pushing a package to pip or something like that. This is a huge commitment. And so you're not just running, extensive unit tests over this thing. Often you're looping in these kind of what's called formal methods, or formal tooling that's actually doing mathematical proofs over the code, things like that, to really make sure it's right. So testing is far more rigorous. That's a big one. And then let's say deployment. Deployment looks completely different because, you know, a chip comes out. Very cool. Yeah, at the other end, at the end of this process, there's a chip. Um, so you're not just like deploying software for somebody to pull it from GitHub, but you're actually producing a physical object. And there's many, many, many layers of the programming stack that actually deal with the physical design of the chip, and it all kind of blends together in this way that just doesn't really exist in software. Maybe you can kind of think of it as like um, you as a if you're a software engineer, it's you're writing code to be run on the machines, but then there's somebody out there, an SRE or a like a more of an operational level person who's making sure the servers are set up, making sure they're running, and they have their own code that runs. They write their own code to make sure that those server farms are working and that your code is running. So you can kind of think of it like that. There's many layers of the stack here. Okay, so highest level, we've got Verilog versus software, um, talking about what hardware development actually looks like, how it's different, how it's similar. So let's just take a really simple. Let's just start with one topic. This will be kind of my trial topic for this video. Um, in the world of hardware versus software languages, hardware versus software. The easiest place to start, kind of the most obvious symmetry between the two, is modules versus functions. Yeah, again, my handwriting is really terrible, so just apologies. Um, so modules versus functions. And before I offend anybody on either side, let me just say, like, flat out, in the end, modules are not equal to functions. Functions, there's an N in there. Modules aren't functions. They're two different things. I just want to say that because I'm going to start drawing analogies, and these analogies will be useful. There are a lot of analogies, but I do want to just be clear that modules are not functions. They're two different things. In fact, we're not going to talk about this because it's just going to confuse things, but Verilog has functions itself. It has a function keyword. Let's not worry about that for now. Pretend I didn't even say it. But we're going to kind of, the reason I want to talk about modules versus functions, modules as functions, as being similar to functions, is because they're both kind of the fundamental logical unit in both of these types of languages, in hardware languages and in software languages. If you want to do something in software, if you want to build something in code, what do? You're going to write a function. If you want, similarly, if you want to build something in hardware, you're going to write a module. You can also maybe make the argument that modules are like classes in code. That's also a valid argument, but I think it's a lot easier to let's just think about them as functions, and we'll talk about why. And I'm given that this is just a trial video, I'm gonna just do kind of a really 10,000-foot view here. I would love to drill into this, and I think doing this video is gonna help me figure out what's worth talking about. But maybe the best way to let's start. The best place to start to give the 10,000-foot view is that the fundamental difference between software and and hardware, sorry, software on this side, hardware on this side, is that hardware languages are producing a chip. So I say area here. The outcome is something physical that takes up space. It's this, actual object. And software on this side is something that runs over time. This is it's immediately incredibly conceptual, so I'm sorry if I lose people here. I'm thinking through this live. But software is something that exists in time. And so, let's say we have like we're calling this function f. And similarly over here, we're instantiating a module called f. Well, how this plays out is that in the length of our program, let's say this is our program P, in the length of our program, there's going to be some block of time in which f is executing, right? And then similarly over here, this is like our design D. There's going to be some span of space that f is taking up. And so if you really think about like the fundamental uh, unit of hardware as being space and not time, um, then the analogy between a module and a function uh, holds, because what calling a function is doing in the software world is it's taking up some, finite amount of the total time of the program. Um, the program is something that exists over the span of time, and the function is just one part of that. It's just one component of that. And so when we division our program up, we're kind of chopping it into blocks of time, and then one of those blocks of time is us running the function f. Similarly, a hardware design, if you think about like all of the Verilog code in a hardware design, what it's really describing is it's not describing something that happens over time. It's describing a physical object that takes up space, that takes up some 2D space, really a 3D space. Uh, and so when you instantiate a function or a module f, and we don't say call a module, we say instantiate, but they're really kind of equivalent. Why don't we write that down as a connecting point? Instantiate versus call, and also like we've said here, space um, versus time. So when we instantiate a module over here in our design, well, it's taking up some finite amount of space. So if our entire design is just a bunch of space, some 3D, 2D or 3D area, then you can think of f as being a subcomponent of our design as just taking up some finite amount of that space. So that's one of the interesting, oh no, so annoying. That's one of the interesting parallels here. Time versus space, and what a function actually means when to be taking up time versus taking up space. That was, really, really high level, but that actually starts to get at one of the paths we can walk down here. This core thing, and this is actually core to like thinking about hardware and why hardware is fundamentally different from software, is that everything in a hardware design, wow, my handwriting, everything in yours, everything in your Verilog exists at all time. This sounds like a weird statement, but this is one of the things that actually makes Verilog hard to wrap your head around, but also conceptually much easier once you understand it. Because if you're reading Verilog, you can put asterisks on this, but if you're reading Verilog, everything that's instantiated in that design exists. It's there. It's in the chip. If you're seeing it, it's there. It's not like it's here at one time and it's gone at another time, because there's no concept of execution, right? Execution is a software concept because, like we said, our software exists in a period of time. This is the time that it's executing. It starts at some time 0 and extends to some time t, and after that it's gone. But our chip, it just exists. It's there. It's printed on a piece of silicon. And so everything that's in that design is actually describing something that's on the chip. It doesn't like get called, run, and then go away. That's not how this works. So that is a fundamental difference. And so like maybe boiling this down to the modules versus functions case, a module instantiation always exists. It does not terminate. And I'm going to put terminate in quotes here because like terminate really doesn't mean anything in the world of hardware. Remember, the chip exists. It's static. It's just there. It's just, you know, a baked piece of sand. Uh, and of course, we're getting dynamics out of it by running electricity through it and all these little devices on it. They're switching on and off. But the chip itself, everything described in the Verilog is just there. On the other hand here, in software, functions begin and end. Oh, I promise I'll have this fixed eventually. Functions begin and end. And this is actually like what's hard about software. Uh, because beginning and ending makes things complicated. Very complicated. Little frowny face. What do I mean by beginning and ending? That's such a generic term. Beginning and ending, you could really say, is basically anything. It's like parallelism, concurrency, uh, recursion, uh, function dominance, or just the concept of dominance in compilers in general. There's all these things here uh, that that are kind of key to reasoning about software. And the whole point of software is that it's like many operations running over time. And reasoning about software, if you've ever tried to reason about a complex, like a React app or like a classic sorting algorithm that you're writing, the hard part is, when does one thing begin? When does the other thing end? How do I order these things? It's kind of the hard part about software is that it's existing over time. Uh, Functions get called. You don't necessarily know when they get called. In hardware, things are a lot simpler. There is a tree of module instantiations, and those modules are there. They don't turn off, they don't turn on, they're just there. So that's a big difference here is, you know, modules always exist versus functions begin and end. And this is actually just kind of a consequence of what I was talking about before, about there being this kind of time, space versus time uh, analogy between these two. Modules always exist in space, but they exist within specific regions of space, right? Functions begin and end when we think about time moving. Um, in some sense, if we thought about, let's extend our timeline here. If we thought about, time, we could see all of time all at once, then we would say, no, that function is always here and that function is always there. But we perceive time instant by instant, right? And so we're either, in this function or we're in that function at a given time. Whereas in space, we perceive space all at once. And so we can say, this always exists and this always exists. Um, Obviously, this is getting a little metaphysical and not quite useful, but I'm hoping this makes sense to you at the highest level. Um, so I would like to do more of these videos and start actually looking at some Verilog code. Um, but I think for now, I'm going to leave it here, just this really high conceptual level. And thanks for listening.